Welcome to Lecture B3 on Gauss Elimination. This is a topic that's already been discussed a bit in this course, so we'll hop right into this and move somewhat quickly, but hopefully not too quickly for you. So let's look first at the following system of equations. X plus y plus z equals 6. X plus y minus 2z is equal to 3, and 2x minus 2y minus 2z equals 0. When we put this system of equations into augmented matrix form, we have the following. The top row becomes 1, 1, 1, 6. The next row is 1, 1, negative 2, 3. The next row is 2, negative 2, negative 2, 0. And now we're ready to proceed with Gaussian elimination. Remember, we start in the first column, and our goal, here is our main diagonal. And our goal is to eliminate all the non-zero terms below the main diagonal. So that's the 1 and the 2 in the first column and the negative 2 down here in the second column. And the way that we eliminate the 1 and the 2 in the first column is by adding multiples of the first row to subsequent rows. So if we add negative 1 times the first row to the second row, we can get rid of this 1. And if we add negative 2 times the first row to the third row, we can get rid of this 2. So that's what we'll do. Okay. So again, the first thing is to add negative 1 times the first row to the second row. Now that doesn't change the first row at all, so we still have 1, 1, 1, 6 there. When we add negative 1 times the first row to the second row, we'll get a 0 here, and a 0 here, and then negative 1 times this 1 will be negative 1, and negative 2 is negative 3. And negative 1 times 6 is negative 6, and 3 is negative 3. And then add negative 2 times the first row to the third row. So negative 2 times 1 is negative 2, and 2 is 0. Negative 2 times this 1 is negative 2, and negative 2 is negative 4. Negative 2 times 1 is negative 2, and negative 2 is negative 4. And finally, negative 2 times 6 is negative 12, and added to 0 gives us negative 12. Okay. Now, at this point, we have something interesting happening. Okay, again, our goal is to eliminate all the non-zero terms below the main diagonal. Well, here is the main diagonal. And so the only remaining non-zero term below the main diagonal is this negative 4 down here. And usually, because this negative 4 is in the second column, we would get rid of it by adding multiples of the second row to subsequent rows, and namely to this row. But adding any multiple of the second row to this row is not going to help us because the second row has a 0 in the diagonal. So we need to do something called partial pivoting, which means that we want to get a non-zero here in this diagonal, and we get it by switching these two rows. Now you might be wondering, well, why don't we add some multiple of the first row down here? If we took 4 times the first row and added it down here, that would indeed get rid of this negative 4, but notice that it would also introduce a 4 here, so we haven't helped ourselves. But if we switch the second row and the third row, then we do get we do get an improvement. So let's do that. We have 1, 1, 1, 6, and 0, negative 4, negative 4, negative 12, and finally 0, 0, -3, -3. Again, that's obtained by switching the second row and the third row. And notice that now we have eliminated all the non-zero terms below the main diagonal. Here is the main diagonal. Everything below it is 0. And therefore, now we're able to use back substitution to finish our solution to this system of equations. Remember, what we'll do now is write down the system of equations that this augmented matrix represents. So we have x plus y plus z equals 6, minus 4y minus 4z is equal to -12, and -3z equals -3. And we start with this bottom equation. Of course, it implies that z is equal to 1, and then we use back substitution, substituting this value for z back into the second equation, and let's see what that will give us then. We will get minus 4y minus 4 is equal to -12. I get that by simply substituting in z equals 1. And now if I add 4 to each side of the equation, I'll get minus 4y is equal to -8. And that tells us that y is equal to 2. And now we take these values of z and y and substitute both of those back into the first equation. And when we do, we get x plus 2 plus 1 is equal to 6, which means x plus 3 is equal to 6. And if we now add -3 to each side of that equation, we get x equals 3. And so our final solution is x equals 3, y equals 2, z equals 1. And if you substitute that solution back into the original system of equations, you will see that it is correct. So that's an example of Gauss elimination, and we had an extra bonus actually because we also got to see an example of partial pivoting in that example. Let's look at another example that requires partial pivoting. So this, let's maybe call this example 1. And so now we'll look at example 2. And example 2 will be this system of equations. Y plus z is equal to 9. X plus y minus z equals 2. And x minus 2y plus z equals 0. So our augmented matrix representing this system of equations would be 0, 1, 1, 9, 1, 1, -1, 2, 1, -2, 1, 0. And again, as we've already hinted, this is going to be a case where we're going to need partial pivoting, because if we look, here is our main diagonal, and we see that there are non-zero terms below the main diagonal in the first column, namely this 1 and this 1. But we would ordinarily get rid of such terms by adding multiples of the first row to these rows. But of course that's not going to help us here because we have a 0 in the diagonal element of the first row. So this is another case where partial pivoting is required. We need to switch the first row with one of these other rows. Now typically we would switch it with the one that would give us the largest value in the diagonal, but notice that here both of these are equal to 1, so neither one is going to give us a bigger diagonal element than would the other. So we'll go ahead and switch it with the second row. So we'll switch the first row with the second row so that we can get this 1 here up into the diagonal element of the first. Okay, so when we switch the first row and second row, we get 1, 1, -1, 2, 0, 1, 1, 9, 1, negative 2, 1, 0. And now we're in good shape. Here is the main diagonal, and we see that we have two terms here, two non-zero terms below the main diagonal. We get rid of this one by adding negative 1 times the first row to the third row. So when we do that, let's see what happens. 1, 1, negative 1, 2. We didn't add anything to the second row, so it stays the same. 0, 1, 1, 9. And when we add negative 1 times the first row to the third row, we get 0. Negative 1 times this one is negative 1, and negative 2 gives us negative 3. Negative 1 times negative 1 is positive 1, and 1 plus 1 is 2. Negative 1 times 2 is negative 2, and 0 gives negative 2. So that's what we obtain when we add negative 1 times the first row to the third row. And now here is the main diagonal, and there's only one remaining non-zero term below the main diagonal, and that is this negative 3. And we can easily eliminate it by adding positive 3 times the second row to the third row. So let's do that and see what happens. So the first row doesn't change. We have 1, 1, negative 1, 2. The second row also doesn't change. 0, 1, 1, 9. And now we're going to add 3 times the second row to the third row. So we get 0. 3 times 1 is 3, plus negative 3 is 0. 3 times this 1 here is 3, and 2 gives 5. And 3 times 9 is 27. Added to negative 2 gives 25. And now we have eliminated all the non-zero terms below the main diagonal. So we'll go back to the equations represented by this triangular triangular augmented matrix. We get x plus y minus z is equal to 2. Y plus z is equal to 9, and 5z is equal to 25. Of course, the last equation implies that z is equal to 5, and if we then substitute that back into the second equation, we get y plus 5 is equal to 9. And if we then subtract 5 from both sides of that equation, we get y is equal to 4. And now we substitute our values for y and z back into the first equation, and we have x plus 4 minus 5 is equal to 2, which is the same thing as saying x minus 1 equals 2. And if we add 1 to each side of this equation, we get x equals 3. And so our solution to this system of equations is x equals 3, y equals 4, z equals 5. And now let's look at a third example. We're going to look altogether in this lecture at 4 examples, and these last 2 examples are examples of what happens when things go wrong, you might say. And you'll see what I mean in just a moment. Okay, so for example 3, we will have x plus y plus z equals 6. 3x plus y minus z is equal to 2, and minus 8x minus 2y plus 4z equals 0. So if we write our augmented matrix here, 1, 1, 1, 6, 3, 1, negative 1, 2, and -8, -2, +4, 0. Here is our main diagonal. So we'll first eliminate this 3 and this -8, and then we'll eliminate the -2. We eliminate the 3 by adding -3 times the first row to the second row. So we get 1, 1, 1, 6. And then when we add -3 times the first row to the second row, we'll get a 0 here. -3 times 1 is -3, and 1 is -2. -3 times 1 is -3, and -1 is -4. And finally, -3 times 6 is -18, and 2 is -16. Now to get rid of the 8, we will add 8 times the first row to the last row. 8 times 1 is 8, plus -8 is 0. 8 times 1 is 8, minus 2 is 6. 8 times 1 is 8, plus 4 is 12. And 8 times 6 is 48. So this is what we have. We've eliminated all the non-zero terms below the diagonal in the first row. And now we have one remaining non-zero term below the main diagonal, and it is this 6. And we can eliminate that by adding 3 times the second row to the third row. So let's do that and see what happens. We get 1, 1, 1, 6, 0, -2, -4, -16. And 3 times the second row now added to the third row. 3 times 0 plus 0 is 0. 3 times -2 is -6, and 6 is 0. 3 times -4 is -12, and 12 is 0. And 3 times -16 is -48. Added to +48 is 0. And now we have eliminated all the non-zero terms below the main diagonal. And we're ready to write the corresponding system of equations, which is x plus y plus z is equal to 6, minus 2y minus 4z is equal to -16. But then notice that the third equation is just 0 equals 0, which doesn't tell us anything. So there's no need to write that equation down, but now we see that we have 2 equations and 3 unknowns. We don't have enough information. There are infinitely many solutions to this system of equations. So this is what happens when you have a system of equations that has infinitely many solutions. What will happen is that you'll get a row of all zeros in your augmented matrix. When that happens, that means infinitely many solutions. And now we'll look at one last case, and I'll write it down for you and then encourage you to stop the video and try to solve it yourselves first, and then we'll look at it all together. So the last case is this: x plus y plus z is equal to 6, x minus 2y plus z is equal to 3, and minus x plus 5y minus z equals 1. So, as I said, I encourage you to stop the video and try to solve this yourselves, and then we'll all look at it together. Okay, so let's see what happens when we go through the procedure with this. Our augmented matrix will be 1, 1, 1, 6. 1, -2, 1, 3, -1, 5, -1, 1. In order to eliminate the non-zero terms below the main diagonal in the first column, we will add -1 times the first row to the second row and +1 times the first row to the third row. So let's see what that gives us. 1, 1, 1, 6. First, we will add -1 times the first row to the second row. So -1 times 1 is -1, and 1 is 0. -1 times 1 is -1, and -2 is -3. -1 times 1 is -1, and 1 is 0. -1 times 6 is -6, and 3 is -3. Now add the first row to the last row. 1 and -1 is 0. 1 and 5 is 6. 1 and -1 is 0. 6 and 1 is 7. Now, we have one remaining non-zero term below the main diagonal, and it is this 6. And we can eliminate that by adding twice the second row to the third row. So let's do that and see what happens. 1, 1, 1, 6. 0, -3, 0, -3. And then when we add twice the second row to the third row, 2 times 0 plus 0 is 0. 2 times -3 is -6 plus 6 is 0. 2 times 0 is 0 plus 0 is 0. And 2 times -3 is -6. And 7 is 1. Now we have eliminated all the non-zero terms below the main diagonal. And if we write the corresponding system of equations, we get x plus y plus z equals 6. Minus 3y is equal to -3. But now look at this last equation. We have 0 times x plus 0 times y plus 0 times z, which is obviously 0 on the left-hand side. And what's that equal? It's equal to 1 on the right-hand side, which is clearly impossible. And so there is no solution to this system of equations. This system of equations is contradictory, and so there is no solution. And when a situation like that exists, this is what will always happen in the Gaussian elimination procedure, is somewhere along the line you will get a row that is all zeros on the left-hand side, but non-zero. It won't necessarily always be 1. It could be some other number, but it'll be all zeros on the left-hand side and some non-zero number on the right-hand side. Whenever that happens, that tells you that the system of equations has no solution. So that covers Gaussian elimination for the solution of a system of equations. And now let's look at some problems for this lecture. So now let's consider the problems for video B3. The first one is the following. What do we find if we use Gauss elimination to solve this system? X plus 2y minus z equals 0. X plus y plus z equals 6. 2x minus y plus z equals 2. And the possible answers are A, the system has infinitely many solutions. B, the system has no solution. C, x equals 1, y equals 2, z equals 3. D, x equals 0, y equals 2, z equals 4. And the second equation, second problem, B3-2. What do we find if we use Gauss elimination to solve this system? X plus y minus z equals 2. X minus y minus 3z equals 0. 2x plus 0y minus 4z equals 3. And the choices are A, the system has infinitely many solutions. B, the system has no solution. C, x equals 3, y equals 0, z equals 1. and D, x equals 4, y equals 5, z equals 6. And finally, a third question, possibly more than that, but at least a third question will be given in the in-class portion of the quiz. So that concludes our lecture B3 on Gauss elimination, and good luck.